Hello, good morning, good afternoon, good evening, everybody. Welcome to Automotive World. I'm Martin Kyle, Editor-in-Chief at Automotive World. I'm delighted to welcome you to today's webinar. The title today is Managing Automotive Software Complexity and Safety with EB tresos and Arm Cortex R52. On the panel today, we have experts from Elektrobit and Arm who will provide an outline as to how Arm processors and EB tresos can support you in your project execution. So why is this important? Consolidating increasingly powerful automotive functions on a single powerful electronic control unit, or ECU, presents challenges for integrating a growing code base while supporting its isolation and managing updates to software over the lifetime of the vehicle. There's also a need for higher levels of functional safety and freedom from interference, and mixed criticality systems are more common and frequently requested to support function consolidation. Today, then, we're going to hear from Arm and Elektrobit about how to overcome some of these challenges, and we're joined by Jochen Steuerwald from Elektrobit and James Scobie from Arm. There'll be a presentation followed by a Q&A. If you would like to ask a question, please type it into the Q&A box on your screen, and we'll make slides and a recording of the event available afterwards. We'll send you an email to let you know how and when you can access those. That's all you'll hear from me now. I'm going to hand over to Jochen and James for Managing Automotive Software Complexity and Safety with EB tresos and Arm Cortex R52. The floor is yours.
Yes, hello and welcome. My name is Jochen Steuerwald, and I've been working with EB since 8 years, mainly working as a project manager for AUTOSAR service projects, and recently the main focus is the product trainings for both EB tresos and EB Corpus product lines.
So hello everybody, yes, my name is James Scobie, and again welcome to today's joint webinar between Arm and Elektrobit. I'm a product manager working for Arm in our automotive line of business and supporting CPUs such as the Cortex R profile for the automotive market. So today I'm going to start off the presentation. I'm going to talk about some of the trends that we're seeing in the market and some of the challenges that they introduce into the automotive space. I'm also then going to talk a little bit about the one of our Cortex R processors, give a quick introduction about that, and talk about the capabilities it has to support virtualization. Then I'll go and I'll hand over back to Jochen from Elektrobit, and he'll talk a bit more about more widely about virtualization and the tresos embedded hypervisor. At the end of the presentation, there will be some time for Q&A as well, we hope. And as we said, the presentations will be ready and available for those after the webinar. So there's a number of global trends out there that we're seeing. Some of them include things like inclusivity, so making sure that elderly and less fortunate are able to take an active part and have access to services such as mobility. And that can be typically challenging, and being able to enable people to have an active world and active place in the world and take part in a range of activities is one the challenge we see. We also see a higher level of digitization taking place than ever before with big data in all areas of our business and our own personal lives, and that requires careful management and control of that information, particularly around about distribution, privacy and security. Sustainability, of course, is a huge area of discussion. It's important that we protect the environment and help to preserve the planet for future generations and the resources it has. And also urbanization. We see a continued growth of large cities with migration into areas of high density populations. And these big trends are have associated issues with society, and we're all trying to deal with how they might be in many different areas, not least of all in the areas of technology. And the automotive industry has a role to play to help to try and address some of those challenges. The auto industry has always provided clearly an access route to improved mobility, and that is generally widely available. But it can widen its inclusivity to help reduce the environmental impact it has. So in recent years, there has been a huge revolution in the auto industry, and we can expect to see much more of that in the next 10 years, maybe more so than we've seen in the last 50 years altogether. There's been a number of factors which have disrupted that. 4 of those main factors are categorized under the term ACEs. Some of you may already have heard of this, about autonomous, connected and electrified vehicles with shared services. And this is going to usher in a new area of sympathetic transportation and mobility. So it's going to have less impact on the environment. It's going to be available for everybody, not just the young and the fortunate. It can have improved experience and better seamless transportation with support for lower emissions and mobility as a service, consuming and generating huge amounts of additional data in the system. Some kind of examples of those are things like robotaxis, where we see electrified, efficient powertrain systems with connected vehicles being a shared service for everybody to access to provide much more efficient urban transportation. So as part of the revolution, we're seeing a change in the makeup of vehicles. So current high-end cars can have more than 100 ECUs already implemented in them, and all of those take up space in the vehicle. They consume power, they add mass to the vehicle, and they're connected with a web of different connected communication systems to allow them to talk and share information between one another. And that's expensive to implement and manage. For the introduction of ACEs, the complexity is unlikely really to be able to efficiently support that going forward. So current architectures we're seeing being developed further. So in some cases, this has been led by new challenger car companies and providers in the market space, where it's easier for them to do so without having the legacy that many of the established and well-respected players already have. But that's being a trend which is much more widely being addressed, and we're seeing much more of that happening more recently. So the revised EE architecture is leading to the creation of effectively domain controllers, where there are fewer ECUs and they are now having typically higher performance class in those ECUs. They're combining functions together into a single domain that would normally be in separated ECUs or separate controllers. And this also provides some added benefits as well, not only reducing weight and simplifying the overall vehicle architecture, but also being able to provide new functionality. Through sharing of information, effectively software functions can be added that would otherwise be complex, expensive, or difficult to integrate in the existing architectures. So this architectural trend is seen in the EE networks on the slide of the vehicles, and it shows from the left-hand side the established approach which is currently available today, moving over to the right to the different trends that we're seeing going forward in time. So the established architecture has lots of these distributed, different dedicated nodes connected across these multiple networks. Often on flat peer-to-peer communications, and distribute the sensing and control and actuation of the vehicle all around the vehicle. So this is transitioning to domain controllers seen in the center of the slide, an architecture which is related to combining functions together where those functions are common. So this means that there are fewer nodes, applications are being consolidated together, but there's a hierarchy of ECUs in there as well. So typically these large domain controllers connected across the backbone, and then some smaller remote actuation and sensing modes to do just some relatively simple functionality. The exact trend will vary from implementation to implementation, and the level of hierarchy is likely to vary as well. And then finally, the transition on the right-hand side is expected to really be the end point of this transition, where a zonal architecture is implemented. And that's where fewer nodes are consolidating together, and where functions are combined into those nodes where they may have unrelated operations. So they're not related to a specific domain or function, but rather their spatial location in the vehicle. and that demands the need for different types of integration, where it comes from many different sources, where functional safety and the different types of characteristics of that compute need to be managed. And this is a type of architecture which is likely, but not limited only, to be seen in the higher levels of autonomy vehicles, where a centralized controller is likely to exist to manage the overall strategy for the vehicle. So the level of software complexity continues to increase across the vehicle. So high-end vehicles already have millions of lines of code in them today. And that code base is getting even greater as time goes by and as autonomy rises in particular. Even on the face of it, seemingly more complex systems like the 787 on the left-hand side have less lines of code, less code to manage. Things like the Large Hadron Collider also, even the back-end code for Facebook. I think areas where you would naturally expect it to be high levels of code are still smaller than that of high-performance processing networks within vehicles today. So as we move closer to autonomy, that level is going to increase significantly higher as well. And importantly, that software comes from lots of different sources and needs to be integrated efficiently together. So there's an industry of software ecosystem suppliers, all delivering based on their expertise and specializations and capabilities. So the operating system, machine learning libraries, the code that comes from the chip makers related specifically to the hardware, the tier 1 subsystem software, the application integration and diagnostics coming from car makers, all of those coming together in a large complexity of the software. And adding to that complexity is the need in many of these systems to introduce elements of functional safety and security within that system, and being able to support mixed levels of criticality as they are integrated together. It will be an increasing trend. These all come together to create this one complex soup of code that's essential part of the delivery of the vehicles that we all expect, both today but increasingly in the future. So Cortex R52 has been developed to address the requirements of these next generation vehicles. So it can be applied to classic automotive applications such as powertrain and chassis control, but also for ADAS and autonomous systems to provide a high-level, real-time safety island with the compute performance necessary to meet those markets. So the increasing trend in software complexity and application consolidation, together with this rise in safety, can be addressed by the R52 processor we just talked about, and helping to reduce the cost and complexity of integration as the price of software development of the overall vehicle continues to rise over time. So the R52 is the first V8R processor from ARM. It introduces features to support virtualization, enabling a simpler separation of software for safety and security functions and assisting in applications consolidation. So the processor is now available as part of the collection of IP in ARM's Flexible Access program that is intended to simplify access to IP licensing. It has new advanced features to support functional safety for detection and management of random faults, as well as support against systematic errors, and it makes it suitable for use in systems with up to ASIL-D requirements. The processor itself delivers a real-time high-performance multi-core platform with the ability to have up to 4 superscalar cores within a single cluster, and also implements the Neon Advanced SIMD extension to provide higher vector compute performance for the system. So it's got comprehensive support to enable tuned deterministic responsiveness for the overall application, and that's through its level 1 and level 2 memory system. So this slide provides a representation of the different types of code that we might be seeing combined together into a single system. So in many classic automotive applications, It would be a composed system where the different functions would be tagged to an individual processor or node, rather than the need for dynamic allocations where functions would be allocated at runtime and would be dynamically identified. So importantly, in some of these systems, there's a demand for virtualizations of tasks where consolidation of application with mixed levels of criticality are needed, while at the same time maintaining real-time determinism. So you may have an ASIL-D, an ASIL-B task, you might have security-related tasks as well, and software related to different applications and coming from different sources. It also, having this type of system means that you need to protect one piece of code from another, predominantly related to the functional safety ASIL rating, but also related to security and indeed just for general IP protection. By being able to protect that software and to have freedom from interference, it allows you, for example, to make code changes with less impact to the rest of the system without the need to do some additional assurance of the separation. So, for example, you might be able to change some non-safe safety-related code or some secure code without the need to go through a recertification process. By being able to separate the software and be able to prove that that separation exists. It's also useful for making updates to the code, so over-the-air updates and changes helps that management. So rather than completely updating the entire image, you can update sections of the image periodically. So the R52 supports virtualization through its multi-stage MPU and different exception levels. So by using this approach, it enables virtualization, but with the ability to rapidly switch contexts, and that's really important for lots of systems where determinism is important and real-time responsiveness is important, and they're not normally available in solutions where virtualization is offered. So this is very valuable for many of the systems where that overhead is a cost or a tax in the system, either having to demand additional performance to guard against that, or being sometimes more challenging to assure in the overall system. So the V8R architecture introduces this new exception level, so EL2, and that's where the hypervisor would reside. And this has the highest privilege level of the processor and is used to manage the guest sitting at the lower exception level 1 in the system. The hypervisor has its own stage 2 memory protection unit, and that's used to configure the protections used by that hypervisor. The guest has its own stage 1 MPU, and that guest and user code protection is enforced by a combination of the allocation of the stage 1 and stage 2 MPUs. This combination of the hypervisor added to the additional exception level and the 2 stages of MPU to provide separation of the software is important to assure freedom from interference and functional safety. It also allows an alternative approach to be used where rather than having a hypervisor, you could just install some high priority code dealing with real-time deterministic tasks or safety-related tasks, anything that needed to be executed with the highest priority to sit at that high exception level. So the processor also provides protection in both the spatial and temporal domains. The MPU itself, of course, provides spatial protection, guarding against data corruption or unpermitted accesses taking place. It prevents execution of restricted code from different virtual machines, and it enables secure and safe protection of the assets. But R52 also has some other mechanisms to guard against temporal faults. So, for example, it includes protection against the interconnect, so detecting if there are any transactions which are incomplete by them not being completed and not happening in the time that they should. But it also prevents against events like live or deadlock taking place, potentially through some of the error handling mechanisms within the processor. And it does temporal protection also through virtualization support, helping to prevent overruns having an interference between different tasks or different virtual machines. So this slide tries to show an example of that. So here we have two different operating systems, RTOS A and RTOS B. They are time sliced between those RTOSes, each of them allocated some particular element of the resource, and the context switch is managed by the hypervisor. In this particular example, we're seeing a system event take place and causes the user level tasks under RTOS A to be extended beyond their expected time. So in some systems that could result in potential challenges if that overrun affected RTOS B and that RTOS B was doing something that was safety related or had a particular criticality with respect to determinism. That could be a real challenge. Here we're showing some slack, so normally that wouldn't be a problem, but often there'll be some tasks where there's less opportunity for slack and you need to do something in a particular predefined time. So in this case, the hypervisor can be used to manage that. It can take over control, prevent RTOS A overrunning and overlapping the RTOS B activities, and reschedule that for a later time slot, assuming that the priorities are can be appropriately done. So I'm going to stop there. I've talked about some of the trends and about the Cortex R52, its virtualization support, but I'll hand over now to Jochen, who will continue the webinar and talk more about hypervisors.
Thank you, James. So I'm not sure, do I have presenter rights? Yes. I will pick up from the challenges of increased software complexity that you have mentioned earlier, James. The first factor to this increased complexity is definitely the increased functionality in the vehicles. So more systems need even further ECUs to control them, and this has also been the main motivation for establishing the automotive open software architecture, also known as AUTOSAR. Nevertheless, applying AUTOSAR concepts alone sometimes is not enough, and basically because we have additional requirements, or we also call it challenges here, which are not in scope of AUTOSAR, or not enough. So let's start with the parallel development. The software is typically developed by independent teams and even independent different suppliers. This somehow is difficult to manage in a traditional ECU because of the required integration. Then we have homologation, which is also an important topic and requirement to the OEMs, that some parts of the software must be frozen earlier than others, so they can be approved by the authorities. So one example are the OBD-related ECUs. Then, of course, we have the mixed criticality, so different ECUs have to fulfill different safety criteria. We have this situation already inside one single ECU and, of course, across all ECUs in the vehicle. So the last point, reusability, is also one of the main motivations for AUTOSAR, but now we do not only talk here about reusability of single software components, but also on an ECU level. So reusing already approved or proven ECUs in a new setup or in a different vehicle is another use case. And so all of these challenges need to be coped with. So the solution side here looks like the following. We have somehow to merge, and we aim here to merge physically separate ECUs into a single one. And let's introduce here a term we are using to describe this merger. We call what has been previously running on a ECU now a self-contained software part, or virtual ECU. And the challenge is here, the exactly way how to merge different virtual ECUs on one physical one. So essentially, there are two strategies to do this. On the left side, you see the situation where we have more hardware resources available on one microcontroller, and we can run the two ECUs on it, so the virtual ECUs on it. They have to be separated by a bus level separation kernel, and this bus level separation kernel then isolates not only the cores but also memory peripherals from the ECUs which are running on it. So that is the case when we have enough cores available, and each of the virtual ECUs gets allocation of the cores here. On the right side, you see another situation where the resources have to be shared. So again, we have two virtual ECUs which we want to merge onto one physical ECU. And in this case, the two cores which are available on the hardware need to be shared because each of the virtual ECUs was developed assuming two cores being available. So here the runtime hypervisor is responsible to schedule the virtual cores on the physical cores and isolate them, and also to some extent to virtualize the peripherals. So our product in this scope is called tresos Embedded Hypervisor, and it is built on the best of both worlds. So we provide a bus level and a runtime hypervisor in one product. So very briefly about the features. When we have a bus level separation kernel available, then it's really possible to virtualize the ECUs and even reset these individually. Of course, we have here also the support of the spatial freedom from interference. The different ASIL levels can be achieved. And also here the embedded hypervisor would take care of some part of the integration of the OS startup, so there's less criteria needed to check before the safe startup scenarios. The runtime hypervisor features allow to have really two virtual ECUs running on the same cores. So that's the main feature for this type of hypervisor. And as we will see in the following slides, there are different scheduling algorithms possible in this kind of scenario, and the embedded hypervisor will support several ones and makes it possible to configure them according to the different needs in the specific application. Now let's have a look how the implementation is done for the Arm Cortex R52. So here again the picture James was explaining before with the introduction of this additional exception level 2 hypervisor mode, and exactly this is now what we use to implement the software part for this embedded hypervisor, and it is using also the underlying exception level 2 memory protection unit. And the other exception units, EL1 MPUs, are still used by the respective guest OS which run on top of the hypervisor. So once again, now the focus is on the runtime hypervisor, because this is the strategy or the concept which is implemented right now for the ARM device. And we see here again the picture, the two different virtual ECUs. And you see that each of them has two cores, and now we call them virtual cores, and underneath the hardware provides also two physical cores. And just to emphasize here, the behavior is that the runtime hypervisor will either allocate the resources to the virtual ECU1 or to the virtual ECU2, but the two virtual ECUs will here not run in parallel. So this is a special setup for the runtime hypervisor. Of course, it doesn't stop with challenges. If you want to implement such a concept, there are a few things to take care of. Let's start with the virtualization of peripherals. Here, the way to proceed, at least on these embedded devices, is that we will virtualize peripherals where absolutely needed, because with each virtualization of peripherals, also the complexity again increases, and also it makes the worst case execution time analysis more difficult. The other challenge is really the scheduling itself, because we are still talking here about real-time system scheduling, so we need a deterministic behavior that's required. And so the main question always is here, what is the impact on the worst case execution time and response times when now the physical resources are shared between two virtual ECUs. The main two strategies here are time slicing and fixed priority scheduling. So time slicing concept defines predefined portions of the execution time for each of the virtual ECUs. And that is one approach, and the other one with a fixed priority is to assign different priorities to these virtual ECUs, though that it is allowed by one of them to interrupt the other one. What we believe is here that the real solution could be to combine both concepts, and this is illustrated in this little diagram here on this page, where the two cores illustrated here are actually virtual cores, and the blue one belongs to the higher priority virtual ECU, and the green one to the lower priority virtual ECU. Though they have time slices assigned, but still the higher priority virtual ECU, when it is, for example, handling an interrupt here, it is allowed to exceed the time slice until it is finished or until the allocated time budget for it has been exceeded. Whereas the lower virtual ECU, when it requires or gets an interrupt, it has to wait until the next time slice for it will occur. So that are not the only two possibilities and strategies here for the scheduling, but at least those which we now consider that they will be used. And again, the specific strategy to be implemented for a certain ECU development needs to be determined and therefore also configured individually. This picture shows now a combination. As I said, we have in the EB tresos Embedded Hypervisor both concepts of virtualization implemented, and as you can see here, also a combination of both is possible. It all depends on the hardware and its features, and also of the number of cores available. So here in this picture you see now two virtual ECUs using this bus level separation hypervisor concept. So each of them have a fixed assignment of cores which they can use permanently, backed up by this bus level separation. And on the right side you still see the two virtual ECUs which both share the same cores. So even these kind of scenarios can be thought of when implementing such an ECU. Let's have now a look at advantages, disadvantages of using this kind of hypervisor. What we do achieve here is that less hardware is needed, and that was one of the main goals we discussed at the beginning. Number of ECUs should be reduced. Also, the hardware utilization will be better. So at least when you try to combine two ECUs into one, where both of them have not utilized the complete computation power of the microcontroller, combining two ECUs can utilize the hardware better. We have virtual ECUs that can also completely be developed and flashed separately. That is also one of the requirements we were talking about. And of course, the spatial freedom from interference is given due to this support from the hardware, in particular due to the EL2 level MPU. On the disadvantage side, we have to be aware that here this concept really interferes with the real-time behavior. There are some constraints to be considered, and especially the worst-case execution time calculations are getting more complex. Also, some virtualization overhead is of course needed due to the switches that take place. In addition to that, that also has an impact. So all the timing behavior needs to be considered, and therefore the reusability here is not green, but in orange, to just remark that this is something to have a close look at when these concepts are used. Yeah, getting already to the conclusion and summary. So it has to be said that the usefulness for each kind of hypervisor in automotive applications is very use case specific. So it's definitely not a solution now for each and every ECU in the vehicle. But if the use cases do allow it, it really does make sense. Also, we see that the hardware support is currently really emerging. So more and more controllers, microcontrollers for the automotive field are now providing also the required hardware support that these kind of hypervisors actually can be implemented. And what we also have seen is that the scheduling of virtual ECUs is something challenging. So we have to deal with several concepts here and decide case by case which one to use. Our product, the tresos Embedded Hypervisor, allows tailoring, so specifically to use cases depending on safety levels, time criticality, and so on. The behavior can be tailored. It supports real-time behavior. That's also the reason why it's part of the tresos product line, where we of course deal with ECUs which require real-time behavior. And also it supports really the utilization of the hardware to a high level. And with that we see this additional challenges described earlier covered. With that, I'm at the end of the presentation, so I hand over again to Martin to have a look at the questions that we got. Thank you very much.
Thank you very much. Thanks both for your time, sharing your insight with us today. As trailed, we do have a question and answer session now. If you'd like to ask a question, please type it into the Q&A box on your screen. We'll put those to our expert speakers. Let's begin here. Is it possible to also run dynamic operating systems like Linux on top of the tresos Embedded Hypervisor?
All right, I will take this question. It's actually not possible because for this use case there is a different hypervisor available, not the tresos Embedded Hypervisor, but we do have a different product line, which is Corpus, which is covering all the adaptive AUTOSAR standard. And as we here deal with dynamic operating system, there is also a respective hypervisor available for this kind of ECUs, which run adaptive AUTOSAR, and this is called Corpus Hypervisor. So there it is possible, but not for the tresos Embedded Hypervisor, which we talked about today.
Okay, and will the tresos Embedded Hypervisor be ASIL certified?
Well, this of course depends. In principle, we plan that this will happen, but it's not. The efforts have to be really considered here. Nevertheless, depends again on the safety level of the ECUs that are running on top of this hypervisor. If it is required, of course, then also a certification of the hypervisor will be done, and this is of course possible, just as it is for the other safety products we have.
All right. How's the configuration of the EB tresos embedded hypervisor? How's that done?
The configuration is done just in the same way like all the other EB tresos modules. So for those who are familiar with the AutoCore, which is our implementation of the AUTOSAR Classic standard, they will know that there is a tool, EB Treso Studio, which allows to configure all these modules. And so the technical background here is that there's a plugin available for each of the modules to be able to configure it and to let the code generators configure the correct code for it. And there's no difference here with the EB Tresos Embedded Hypervisor. It will also come as a plugin for the EB Treso Studio.
Okay, I've got a question for Arm here. Does Cortex handle natural language processing, NLP, for commands?
So the Cortex R52 implements the ARM V8R instruction set architecture, so ARch32 for Thumb and for Thumb2, and 32-bit instruction set has extensions for Neon, the SIMD instruction set. So a lot of that Neon and the vector extensions allows you to support improve enhancements in terms of the DSP operations, which can be used as part of NLP type execution code. So that can be used for that type of workload.
Okay, and I'm not sure who wants to take this. Are there any AUTOSAR requirements for the use of hypervisor?
As I would try to just comment on this. So as far as I know, the whole hypervisor topics are not covered by any of the AUTOSAR requirement documents. So this is still something up to the different software suppliers to come up with both the requirements and the solution for it.
I think it'd be interesting at this point to step back a little bit from the technical details and talk a little bit more broadly about what we've been dealing with here, which is the consolidation of automotive functions onto single powerful ECUs. Can you just talk a little bit more generally, please, about the benefits and the complexities and the challenges of doing this? Obviously, there's talk of over the years, recent years, there has been talk of how this both makes a vehicle more vulnerable, let's say if there was an attack on the ECU, but that it also enables better defense against attacks because it's only in one place rather than in numerous places. So that's just one thing that I've got at the back of my mind when I'm asking that question. What are the automakers and the suppliers talking about when they're approaching the idea of these powerful single ECUs?
So if you like, I'll start that question off. So I think there's a range of benefits of the change of the architecture, not least of all because the challenges of adding the additional complexity that are currently being integrated into vehicles today. So autonomy is one of many of the trends which is doing that, where there's a higher demand for compute. But things like the domain controllers that we talked about, where you're combining functions together, you're being able to provide a better view of the overall activity that's taking place in the car, being able to communicate that more rapidly. So controlling all of the lateral characteristics of the vehicle all together at one time in one place, as opposed to being distributed with its own separated systems doing part of that work. And by combining them together into a single system, you are having benefits of weight, of packaging, of area, of potentially of cost. But that comes with some complexity too. So certainly the systems that you're implementing need to be higher in performance to be able to account for that. And you are combining these applications together, which have been established and developed often in isolation, or to a greater degree in isolation from one another, and being able to integrate them together takes a significant amount of amount of effort, and therefore being able to maintain and keep software partitioned is one of the methods that you can use to overcome those sorts of challenges. By having fewer of those nodes and integrating more functionality together, you can take advantage of, as you say, potentially applying a different layered security approach to the overall vehicle and managing that, and what resources are distributed around the car can be somewhat more constrained. I think that there certainly are some vulnerabilities, but being able to have that layered approach helps you to be able to address some of those. Other challenges, of course, are the type of compute that you're going to apply within those nodes. So you have demand for high throughput. There are some applications that need the determinism real-time that we've been talking about today. Some systems need higher levels of functional safety than others, and again, combining them together into a single system can be a real challenge. So being able to, once again, separate them, partition them, and be able to allocate the right type of compute resources to deliver that, rather than necessarily a one-size-fits-all, is we think the right approach to take.
Great, thank you. Jochen, have you got anything that you want to add to that? I'm thinking perhaps more from a software perspective.
Yeah, when I think about the challenges that come on top of that, what we have talked about today, it's of course also the responsibility of the final physical ECUs, because if we integrate more and more different software parts on one physical ECU, the challenge is not just to integrate this. Of course, this is already a technical challenge that has to be dealt with, but also at the end, when things have to be resolved, who is responsible for it? As we have now a huge chain of different suppliers that contributed to different software parts which are running on this ECU. So this might also be one of the reasons why the actual doing and of this concept will take longer than expected.
Great, thank you. Thanks for sharing that. Question here about the SOCs. Which SOCs does the tresos hypervisor support? And then there's a couple of supplementary questions. When will it be available, and which devices are virtualized?
So currently, the EB tresos Embedded Hypervisor is available for two different hardware platforms. As a development stage, we aim to finalize this as a product with manufacturer availability early next year. But basically, the only requirement to be able to port this on a different SWC is really to have the hardware features available. So either these which are required for this runtime hypervisor concept, like on the ARM, or on the bus level. So in both cases, there is some hardware support required. And as I said earlier, hardware support is also emerging, so I expect that this will be available on more and more devices in the future. And so it can be ported as long as the hardware support is provided.
Okay, great. Well, thank you very much. I think we've worked through the questions that are coming from the audience there, so I'd like to thank you for taking those questions. Thank you to everybody who dialed in today and joined us for this webinar. We will be sending out an email with information about how and when you can access the sliding and on-demand recording of this event. I'd like to draw the session to a close. Thank you very much, and we'll see you at the next Automotive World webinar. Goodbye.